each word has a number or a set of numbers. In fact, there can be very long sets of numbers, like 300 dimensions. But what do we make of a sentence? The early mathematical models of language did sentences purely as an average of words or a sum of words. That's a little bit, that worked, but in some cases it will not work. For example, you have two words that are opposites, they're going to cancel out. You get nothing. So it will not understand a lot of these relationships. But there are new kinds of models that are developed by Google and other entities called transformer models. You will hear that. Really, these transformer models, when you think about this, especially for those of you who can know a little bit about math, but you shouldn't think about complicated formulas. And this is where, in general, neural networks are fascinating. The math is not complex. In fact, you let the computer do the analyzing and you never write down the math. I mean, if you could write down the neural network, it would be an immensely long equation, but we never do. So in some sense, AI is not about math, right? You do need to understand what you're doing, but it's a lot more about various computing tricks. And you see here, you have different words. So this is translation. You have words, and then every word is connected to every other word, up, down, back, forth, and so on and so forth. And then there's a generates translation. Every one of these little things is being trained, right? They're called neurons. They're being trained to do a translation, and there's a huge interconnectivity between them. What I'm trying to get here is that not that you have to memorize this, but you start with very simple concepts. Numbers, words have numbers, and they have relationships: king, queen, man, woman. Then you go next to sentences, and you can make this really, really complicated. But at its core, it's nothing more than what I showed you in previous slides, right? It still goes back to these relationships, right? It finds relationships. It just does it in a very kind of dense net, but it is not fundamentally different. Neural networks are very vulnerable. In fact, I will show you. What does this picture say? Well, you have a panda and a panda. You can take something that the neural network knows and add a little bit of noise. You see this 0.07, it's just a very small, you multiply this picture. And then all of a sudden, so the model knew that this is a panda. It had 60% confidence, but you see, you add just a little bit of noise, and now it says with 100% confidence that this is a gibbon. When all you have is just really a panda. I mean, this picture is barely different. What's amazing here is that this is not a fluke. You can actually generate these examples. In other words, you can write a machine that will specifically exist to trick a neural network. That is why I will tell you, I'm very cautious about using these types of machines in cases where you have adversarial relationships or security issues, because these models can be tricked. What they found is that almost all of the models that exist now, they're subject to this problem. In order to avoid this problem, you need to train much bigger, much longer models that the computing power has to increase tremendously. And it's not increasing as much. Moore's law, computing power becomes basically cheaper by 2x, every 2 years. And so the Moore's law is basically says that you're going to get more and more powerful computers over time, and they're going to cost less and less. That's no longer true, by the way. There's going to be physical barriers there. And the problem is that you can train one or two or a few models to avoid this problem. You can't train them all with very complicated models. This problem exists. And if you want to trick a neural network, you can.